The ultimate objective of open-ended AI is to build systems capable of autonomously accelerating their own problem-solving abilities without human intervention. To achieve this, an AI must learn to improve its own learning processes over time. Current hierarchical agent architectures fail to achieve this because they rely on fixed, handcrafted meta-agents. A meta-agent acts as a supervisor, modifying a base agent to improve its performance. However, progress halts the moment the base agent reaches the boundaries of the meta-agent's original human-engineered design. The meta-agent cannot evolve. Attempting to fix this by adding a meta-agent to optimize the meta-agent merely shifts the bottleneck upward. It requires a meta-agent to optimize the layer above that, resulting in an infinite regress of static levels. Because the mechanism of improvement remains outside the system's control, the architecture enforces a definitive ceiling. Progress is capped by the limits of the initial human design. The Darwin-Gödel machine with Hyperagents, or DGMH, solves this bottleneck by unifying both the task agent and the meta-agent into a single, editable Python program. This creates a capability called metacognitive self-modification. Because the system is self-referential, it has permission to rewrite the exact code that determines how it learns. In standard hierarchical systems, the editable perimeter only encompasses the base agent executing the problem. In a hyperagent architecture, that editable perimeter expands to include the generation of future improvements. By placing the meta-agent inside the editable boundary, the AI optimizes both the specific solution to a given task and the foundational algorithm it uses to discover those solutions. The original Darwin-Gödel machine modifies its own code, evaluates variance, and archives successes as stepping stones. But the critical bottleneck is its instruction generation mechanism, a fixed, uneditable block dictating exactly where the agent improves. This creates a strict alignment problem for the system. The original DGM successfully improves at self-improving because both task and modification are coding-based operations. If the task domain shifts to non-coding problems, like robotics or poetry, the DGM's fixed meta-mechanism collapses. The skills required to evaluate a poem or simulate a robot do not align with the coding skills required to write a better self-improvement instruction. The DGM-H eliminates the fixed instruction generator, merging the task and meta-agents into a unified hyperagent. It runs an open-ended loop where parent hyperagents generate self-modified variants, adding them to an expanding archive of stepping stones. The agent can now rewrite its own parent selection, alter its self-modification logic, and restructure its evaluation protocols. By allowing the improvement procedure itself to evolve, the DGM-H eliminates the assumption that task performance and self-modification skill must be manually aligned. It learns how to improve in whatever domain it is placed. Without manual domain-specific customization, the standard DGM records zero performance on complex, non-coding tasks like simulated conference paper review. But tested on that exact same task, the DGM-H reaches a score of 0.710, exceeding the established static baseline. This chart shows the results for robotics reward design. The agent successfully generated zero-shot physics reward functions that trained a simulated quadruped robot, surpassing the 0.348 performance of the default human-engineered reward function. These scores are not the result of simple prompt tweaks. To achieve this, the DGM-H autonomously constructed explicit multi-stage evaluation pipelines and built internal physics knowledge bases from scratch. What specific algorithmic infrastructure did the meta-agent invent to achieve these task improvements? The meta-agent wrote this performance tracker class to aggregate metrics across iterations, identifying sustained improvements. By calculating moving averages, it built a mathematical mechanism to systematically avoid unproductive modification directions and prevent regressions. The agent utilizes persistent JSON memory to store synthesized insights and causal hypotheses. This specific entry shows the agent diagnosing an overcorrection in generation 65 and proposing a countermeasure for generation 66. The DGM-H built the tools required to manage its own evolution. It autonomously produced the scientific tracking and memory structures that usually require manual engineering. To test if this architecture truly generalizes, we have to see if the performance tracking and memory infrastructure optimized in one domain work on a completely unseen, unrelated task. We measure this using the Improvement at K metric, or IMP at K. It isolates the meta-agent's pure ability to improve task agents by measuring the test performance gain after a strict number of iterations, in this case, 50. This chart shows the failure of standard transfer. A meta-agent taken from a standard DGM run has zero ability to generate better agents when transferred to a new domain like Olympiad-level math grading. This chart shows the Hyperagent transfer. A DGM-H that was previously optimized on paper review and robotics successfully accelerated learning on Olympiad math grading, yielding a 0.630 improvement score. Metacognitive self-modification produces transferable learning algorithms. By rewriting its own logic across disparate environments, the AI learned how to learn. This graph illustrates compounding growth when the DGM-H is initialized with an existing state-of-the-art model, Proof Autograder, rather than starting from a blank slate. The transferred meta-agent successfully improves upon the existing baseline, stacking its autonomously developed improvements on top of a highly capable mathematical model. These systems require strict safety constraints to operate securely. Autonomous modification introduces the risk of unintended behaviors, making sandboxed execution environments, enforced resource limits, and fixed task distributions an absolute necessity during experimentation. While currently bounded by these safety constraints, Hyperagents provide a verified architectural blueprint for AI systems that continually engineer their own intelligence.